Okay, we're here to talk about inductors. Simplest kind of inductor is simply a coil of wire. And about the property of inductor called inductance. We use the symbol L to write inductance, and we know, or we'll learn inductance to be the property that a coil has of inhibiting a change of current through the coil. So let's try and understand that property. Let's draw a coil of wire looking from the side and a coil of wire looking down the end, and see what happens when we try to put current through a coil. So if we put current into the coil from here, it's going to circulate through, or if we have current entering here, the current is going to circulate clockwise through the coil and then out. And we know from right-hand rule number 3 that current circulating clockwise through a coil will give us a field through the coil, in this case into the page or into the screen. You should be able to use right-hand rule number 3 to get that. And if we start with zero current and we have an increasing current, then what we have is an increasing flux. And we know from Faraday's law that an increasing flux results in an induced EMF. And we also need to remind ourselves that flux, in a simple case where the B and the area and the direction is constant, is simply BA cosine theta. And we also want to remind ourselves that B for a coil comes from simply mu naught N over L. You should know all this, times I through the coil, where N is the number of windings and L is the length of the coil. And the N over L can be thought of as the winding density. So what we have here is a changing current, in this case increasing, leads to a changing or increasing magnetic field, leads to a changing, in this case, increasing magnetic flux into the page, and that in turn will induce an EMF. And so given a current circulating through the coil in a clockwise direction and an increasing flux, more and more X's appearing, use Lenz's law to decide which way the induced EMF is going to be and which way it would tend to drive current. So do that. Pause the video and do that before I tell you. Okay, so since the flux in the page is increasing, Lenz's law says you need to oppose that change. So the EMF that is going to tend to drive a current has to drive a current in the opposite direction. It has to drive a current in the counterclockwise direction, which would lead to field lines and a flux coming out of the page, which would tend to prevent the change in flux, the increase in flux that's producing the EMF itself. So the induced EMF is tending to drive current in the opposite direction of the current that's producing that change in flux and that EMF. So it's sometimes referred to as a back EMF. And the net effect is it slows the current down. So we're going to define inductance this way. And let me draw a parallel with resistance. In fact, let me just run through this. Capacitance is the ratio of charge you get to voltage. And conductance in a circuit would be the ratio of current to voltage. But resistance, remember, is the opposite of conductance. Did I say inductance? I meant conductance. So resistance is the inverse of this. Resistance is the ratio of voltage to current. And resistance means the resistance to flow of charge, and we define it this way. So when we come to our inductance, since it inhibits a rising or changing current in a circuit, we can think of it as a kind of resistance. And so we'll define it as the voltage across the inductor divided by, in this case, what causes the resistance is the change in current. And so it's the voltage. Actually, I'm going to change that because the usual way it's written is EMF. So I'm going to change that to, it's the ratio of the induced EMF to the change in current over the change in time. So think about all this. This is important. The resistance inhibits the flow of current. Inductance inhibits the change of current, the increase or decrease in current. So they're parallel in some ways, but quite different in others. So this we will now take to be our definition of inductance, just like we take this to be our definition of resistance. And so remembering the usual format in which we write this, we usually write it as V equals I over R. We can rewrite our inductance equation in that form. We can say that the induced EMF we get is going to be equal to, there's actually a minus sign there because of Lenz's law, L times, instead of I, di dt, right? And referencing Faraday's law equation, we can relate this same induced EMF to the change in flux through the coil. So I'm going to set those equal to each other. So this equals minus N d phi dt. And since both sides have a dt, we can rewrite this equation this way. We can say that L, notice the algebra, equals minus N d phi di. And we can further simplify this to, in a way that we can think of L as the ratio of flux that you get in any situation to the amount of current that's present. So think about the logic of this. If you have a situation where you get a lot of flux per unit current, then you're going to have a high inductance per winding. Now let's go one step further. We have this equation that L equals, I'm going to drop the minus sign, N phi over I. And we're going to expand out. For a coil, the flux through the coil is going to be B times A, and for a coil, the field and the face of the coil are always at 0 degrees to each other, so the cosine of theta is 1. So we have NBA over I, and then going one step further, we get N, what's B? Remember that? Mu naught I N over L times A all over I. So the i's cancel, and simplifying this one step further, doing the algebra, we get that L for a coil, a simple coil, is simply going to be mu naught N squared A over L. So now we know how to calculate what the inductance of any simple coil is going to be from its geometry and its characteristics.